Hi everyone, in this lesson we're going to be looking at the quotient rule. First we're going to be looking at a few examples that you might come across where you need to use the quotient rule, and we'll be doing some more difficult examples at the end. And finally, something of interest, we're actually going to be deriving the derivative for tan of x from the quotient rule. So first of all, what is the quotient rule? The quotient rule is a way of finding the derivative of something that looks like that. Y, or f of x, is equal to u over v, where u and v are smaller functions that we can deal with easily, like e to the x, x squared, sine of x, log e of x, the square root of x. Any combination, or any of those functions with a combination of translations and dilations. So let's have a look. If we have this function where we get in the form y is u on v, then we can apply this rule here. dy dx is equal to v du dx, take u dv dx, all over v squared. And if this is looking a bit crazy to you, just look below and we'll do this example. We have y is equal to e to the x on x, and that looks a lot like this, u on v. So the first thing we do is say, let u equal e to the x, and v equal x. And then we say below that, to fill in this formula here, we need both u and v, and du dx and dv dx. So we say du dx is the derivative of e to the x, which is e to the x, and dv dx is the derivative of x, which is just 1. So now we have all four components to plug into this formula up here. So we started with y is equal to ax on x. We changed that to u on v by letting u and v equal the appropriate terms. And finally we're going to apply this formula, dy dx is equal to v, which is x, times du dx, which is e to the x, take away u, which is also e to the x, times dv dx, which is 1. So this comes to x, ex, take e to the x, which is it. You know what we've forgotten to do here? I apologize for this. In this line here, I used to do this in the exam, I forgot to put it all over v squared, so I'm going to take this and put it all over v squared, so that's all over x squared. So it comes to x, e to the x, take e to the x on x squared, which is equal to x take 1, e to the x on x squared. So let's look at a more difficult example over to the right here. I'll move this over so we have room for later. We start off with the term y equals log e, bracket, 3x take 2, all squared bracket, over the square root of x take 2 plus x. And I've put in this second term in here just to get you to think a little bit, because what we're going to do is deal with these derivatives separately. We're going to find the derivative of this half of the expression, and then find the derivative of this half, and then add them together, just as you do if you had a problem that looked like this. Y equals the square root of x take 1 plus e to the x. You'd find the derivative of this and add it to the derivative of this. So we deal with them separately. So the first term is the interesting one. The second term, well, the derivative of x is going to be 1, but the second term is the one we're going to look at. So log ex, 3x take 2 squared over the square root of x take 2. That is a lot like u on v. And you know what, I'm just going to say, it's a bit different because we can't say dy dx is equal to u on v. Oh, you know what, we can. Let's do that. We'll say dy dx, no. How are we going to do this? Y, that's wrong. Y is equal to u on v, and then on the end here I've just got plus 1. If this is confusing, just ignore it for now, but basically that's the derivative of the term that's hanging on the end. So dy dx is going to follow the quotient rule here. That's v du dx, take away u dv dx, all over v squared. That's the derivative of this first term, and then we've got the 1 on the end. So let's say we want to find what v is, what u is, what du dx is, and what dv dx is. U is equal to log e 3x take 2 all squared, and v is equal to the square root of x take 2. Du dx is equal to, well, this is a bit of a mystery. I say first of all we get rid of that squared inside the log to make it easier for ourselves. So u is also equal to, this 2 can come and be multiplied down the front, 2 log e 3x take 2. So du dx is equal to 2 times 1 over 3x take 2. And if you're wondering why this 3 didn't come multiplied at the front, go check out the video on the derivation of logs, because this 3 doesn't get multiplied out the front. Over here we've got v equals the square root of x take 2, which is equal to x take 2 to the power of a half. So dv dx is equal to, well, you multiply the half down the front, so it's 1/2, and then you take a power off this term here, x take 2 to the power of negative 1 on 2. So now we've got all our terms ready. I'm going to move this up a little. So we can fill in this formula here, dy dx is equal to v du dx. So that's the square root of x take 2 multiplied by 2 over 3x take 2. Take away u dv dx. Let's put u in its simplest form there. Take away 2 log e 3x take 2 times dv dx. Well, that's there, times 1/2 x take 2 to the power of negative a half. And this is all over v squared. So the square root of x take 2 squared. And then don't forget we've got this plus 1 on the end from the x that's hanging out over there. We have to move all this up again. They can overlap a little. So this can be written in a simpler form. This is equal to 2 square root x take 2 all over 3x take 2. Take away, well, this half and this 2 can multiply together to make 1. Log e 3x take 2. We can say all over the square root of x take 2, because that's what that to the power of negative half does, and this is all over x take 2. And this can be simplified down a little more, especially on this side, but I just won't worry about that for now. Whoops, and I almost forgot, plus 1 on the end. So you can see it gets quite complicated, and when you do start plugging this sort of thing into your calculator, this is what you see, and if not more complicated. So the final application of the quotient rule, I'm going to move this over so it's sitting on top of that. Say we started off with y is equal to tan of x. This is equal to sine of x on cos of x, which we'll say is equal to u on v. So u is equal to sine of x, v is equal to cos of x, du dx, or as some people write it, u dash is equal to cos of x, and v dash or dv dx is equal to negative sine x. So now we have the formula dy dx is equal to, and we'll be going off this formula over here, v du dx, so that's cos x du dx, so it's cos x, take away u, dv dx, that's sine x negative sine x, all over v squared, and v is cos of x, so cos squared x. And this is just basically, you can write it another way, you can rewrite it like this, cos of x squared, but I prefer cos squared x. So this becomes now, we'll see how we've got a negative times a negative over here. That means it's cos squared x, well, that's the first term, and then plus, because it's negative times negative, so it's plus sine squared x, all over cos squared x, and this up here is the identity. Cos squared x plus sine squared x always equals 1, so it's 1 over cos squared x. And if you're wondering why that is, if you remembered our, am I getting ellipse here? If you remembered our unit circle, here we go. We said that you draw a line at angle x, the red line, the length of that red line, if this is the unit circle here and there's length 1, the length of that red line is sine of x, and this purple line is cos of x. And according to Pythagoras, the square of this side plus the square of this side is equal to the square of this side, and this side is equal to 1. So sine squared x plus cos squared x is equal to 1.